very strange is happening in the early universe. What did the James Webb Telescope just see at the very edge of time? And why are some scientists claiming these new discoveries could change everything we know? For decades, we've had a standard story of our universe, known as the Lambda-CDM model. This model explains our cosmic history, from the Big Bang 13.8 billion years ago to the vast cosmos we observe today. This understanding was built on a massive amount of evidence and has been our guide for half a century. But now, the James Webb Space Telescope is sending back data that challenges this story. It's seeing things that, according to our models, shouldn't exist so early in the universe's history. These aren't small issues. Scientists are now saying that we may be facing a crisis in cosmology. This means that our fundamental understanding of the universe might be incomplete or even wrong. And the work of Nobel Prize-winning scientists is at the center of this growing problem. So let's think about this. To understand why the new data is so shocking, we first need to understand the story it's challenging. This is the Lambda-CDM model, our standard model of cosmology. It begins 13.8 billion years ago with the Big Bang. The Big Bang was not an explosion in space. Instead, it was the beginning of space and time itself. An infinitely dense point began to expand, and this expansion created the fabric of the universe. In the first moments, the universe inflated at an incredible speed. As it expanded, it cooled. The basic particles started to form atoms, mainly hydrogen and helium. This process released a flash of light that we can still see today, known as the cosmic microwave background, or CMB. This CMB is like a baby picture of the universe, and it's one of the strongest pieces of evidence for the Big Bang. According to the standard model, what happened next was a very slow, gradual process. Gravity began to act on tiny density differences in the early universe. Over hundreds of millions of years, gravity pulled gas together into clumps, which eventually formed the first stars. These early stars lived short lives and exploded, creating heavier elements like carbon and oxygen. From the remains of these first stars, new stars were born, and over billions of years, they gathered to form the first galaxies. Our model predicted that these first galaxies should be small, irregular, and chemically simple. They should look like cosmic infants. For 50 years, this was the accepted timeline. Then, the James Webb Space Telescope opened its eye. The James Webb Space Telescope is the most powerful observatory ever built. Its main advantage isn't just its size, but its ability to see the universe in infrared light. This is important for two reasons. First, as the universe expands, the light from the most distant objects gets stretched into the infrared spectrum. This is called redshift. Webb is designed to see this redshifted light from the earliest objects. Second, infrared light can see through the cosmic dust that hides the birth of stars and galaxies. This means that the JWST is essentially a time machine. When it looks at a galaxy 13.5 billion light-years away, it's seeing it as it was 13.5 billion years ago, when the universe was only a few 100 million years old. It was built to see the first stars and galaxies forming and to confirm our standard story of how the universe evolved. Scientists were prepared for surprises, but not for what the telescope found in its very first observations. These observations didn't just add new details to our story, they began to challenge its foundations. When astronomers looked at the first data from JWST, they found something that didn't make sense. They expected to find small, infant galaxies in the early universe. Instead, they found galaxies that looked more like teenagers or even adults. For instance, JWST has identified galaxies that existed just 280 million years after the Big Bang. Before these observations, it was thought that the first galaxies didn't start forming until 500 or 600 million years after the Big Bang. Let's think about why this is a problem. Building a massive galaxy, according to the Standard Model, takes a very long time. You need dark matter to create a gravitational structure. Then you need to pull in huge amounts of gas, which then has to cool and form billions of stars. For a galaxy to appear mature, it needs to have gone through multiple generations of stars to create heavier elements. Our models suggested this should take over 1 billion years. Yet, JWST was finding massive, well-structured galaxies that formed in a fraction of that time. It's like finding a fully grown oak tree where you expected to see a small sprout. The scientists who made these discoveries rechecked their data, assuming it was a mistake. But the data held up. This means that our timeline of cosmic history is being challenged. The universe either grew up much faster than we thought, or the physics of the early universe was different from what our model describes. This discovery of impossible early galaxies is connected to another major problem, which many scientists call the crisis in cosmology. This problem is known as the Hubble tension. At its core is a simple question: how fast is the universe expanding today? The work of Nobel Prize-winning scientists like Adam Rees is central to this issue. We have two main ways to measure the expansion rate, called the Hubble constant. The first method looks at the early universe. We use data from the cosmic microwave background, that baby picture of the universe, and feed it into our standard model. The model then predicts how fast the universe should be expanding today. This method gives a value of about 67 kilometers per second per megaparsec. The second method looks at the local universe. Here, astronomers like Adam Rees's team directly measure the distances to nearby galaxies and how fast they're moving away from us. They use objects called standard candles, like certain types of stars and supernovae, whose true brightness is known. This method gives a different, faster value of about 73 kilometers per second per megaparsec. For years, many hoped that better measurements would resolve this difference. JWST was supposed to be the tiebreaker. Instead, it confirmed that both measurements are incredibly precise. This means that the discrepancy is real. The universe appears to be expanding at two different speeds. This is a major crisis for cosmology. It suggests that the standard model, our story connecting the early universe to the present day, is missing something important. The model itself may be incomplete. This is the context for the warnings from top scientists. The data suggests we are living in a reality that doesn't quite match the one described by our current science. From the perspective of our models, it's like we're observing another universe's properties. When a successful theory faces a crisis, scientists are forced to consider radical new ideas. One idea is that there was new physics in the early universe. A concept called early dark energy suggests that a temporary energy field gave the universe an extra push in its infancy. This would have caused it to expand faster than our standard model predicts, and could potentially solve the Hubble tension. Another more radical idea is that Einstein's theory of gravity might need to be modified on cosmic scales. If gravity behaved differently in the early universe, perhaps being slightly stronger, it could explain how massive galaxies formed so quickly. But perhaps the strangest evidence comes from a recent study of early galaxies observed by JWST. Modern cosmology is built on the assumption that the universe is isotropic, meaning that it looks the same in all directions. This would mean that galaxies should spin in random directions, with about 50% spinning clockwise and 50% counterclockwise. However, one study found that a majority of early spiral galaxies seem to be spinning in the same direction. This is a very strange result. It hints that the universe itself might not be perfectly isotropic and could have been born with an overall spin. Our standard model does not account for this at all. This has revived interest in a speculative theory known as black hole cosmology. This theory proposes that our universe might exist inside a massive black hole that formed in a larger parent universe. This could potentially explain a cosmic spin, as our universe would have inherited the rotation of the black hole it formed from. This is a very literal interpretation of the another universe idea, that we may be inside an object within a larger cosmos. So, where are we now? We are at the beginning of what could be a scientific revolution.